recording. So, happy Thursday! Welcome back. I had a moment of disorientation on the drive-in just a little bit ago because they were playing Manic Monday on the radio. And I was like, wait, it's Thursday, right? Like, I've only heard that song played on Mondays, like, throughout most of my lifetime. So, just a note to the DJs, don't do that to people. No one wants to think it's Monday when it's not Monday. Goodness. Speaking of Mondays, your next 2 Mondays just got a little better. So I decided to adjust the due dates for formative assessment number 2. Was going to be due Monday, but I'm making it Wednesday because I'm not sure if we're going to get through all the questions today. So to cover my bases, you should be able to do at least half of them after today for sure. The last 2 maybe are going to be iffy. But everything is in the slides, and obviously there's no penalty to being wrong, so you can still try to give it a shot. For the same reason, because I think we're not going to be done with Unit 4, I moved back your first homework to be due Wednesday, October 2nd, instead of Monday, 9:30. That is not yet out. I have released it to the TAs for testing purposes. Once they tell me nothing has been screwed up, I will release it to you. Fair? As I told you last time, this is not a data analysis homework like most of them are. This is a different one. It is a vocabulary drill disguised as math. Okay? So we'll be talking about how many parameters are in each kind of model, how the parameters work together to create patterns, and that kind of thing. So that's what I'm looking for you to be able to recreate in the first homework. All right, one more thing. Tennyson is out today on a trip, so no office hours after class for that. But I figure that should be fine since there's no outstanding work that currently needs to be done. All right, anything I'm forgetting? Logistics-wise, stuff, schedule-wise? No, we're good? All right, since it's still hot as hell outside, I'm drinking lemonade because, I'm just going to lean into this whole summer thing. Why not, right? Until you get inside the building and then it's like, 60 degrees of air conditioning. So makes it fun to figure out how to dress, I know. All right, then let's jump back into lecture 4, shall we? Okay, so big picture slide here. What we are trying to do is figure out what kind of model can best recreate the patterns of dependency in our longitudinal data. Dependency means correlation. It also is going to mean heterogeneous variances, heteroscedasticity as a function of time. And there are many potential choices that you have at your disposal that are built into regular software. There's probably many, many more that I'm not even aware of. I'm going to show you some of the most common ones, the ones that are most suitable for longitudinal data, but all of them are going to fit somewhere on this spectrum from parsimony on the left. The simplest model that would be reasonable for longitudinal data is compound symmetry. And how many parameters does it have? Just 2. If I had 1,000,000 occasions, how many parameters would it have? 2. So this model acknowledges that occasions from the same person are likely to be correlated, but it says that correlation is constant. On the other side of the spectrum is the unstructured matrix, meaning every variance and covariance is estimated separately, so the number of parameters increases quite quickly with the number of occasions. This one requires balanced data as well. Compound symmetry does not. So this unit 4, we're looking at what I call alternative covariant structures, basically different patterns in these matrices. And then we'll be building on that to include additional kinds of random effects in units 5 and 6 and so on. So that's the big picture. We talked about comparisons of model fit last time. We're going to be doing likelihood ratio tests to compare nested models, also looking at AIC and BIC, the computation of which differs across programs to some extent. Then I think where we were. I think we were here last time. I think this is the new stuff, right? Does that look familiar? This is slide 8. I don't recall talking about this, so it's new. How's that? Yeah. You had what? We stopped on 6. Let me go back then. Yep. So you're saying that you stopped at 6, yeah, and I may have kept going. Well, if you stopped at 6, I think odds are good that other folks may have as well. Can we make that assumption, right? That perfect attention the entire time is an unreasonable expectation?
Yes.
Yes, it is. And that's why I record. So if you miss something, you can hear it again. But yeah, let's back up a bit. So there's really two questions that we're answering in comparing models at this point. Are the residual variances different over time or the same? And right now, those are the only two options, all different or all same. And how are the residuals from the same sampling unit, level 2 unit, person in this case, correlated? And there's different kinds of patterns of correlation that I'll introduce you to. And to answer these questions as to whether adding parameters helps, that's likelihood ratio tests. So the difference in -2 log likelihood. And note the formula, this is going to be a series of homework questions. I will ask about 5 questions that say which of these results in a valid likelihood ratio test. Here's one of the things I'm checking for. The order, fewer minus more, is inside. The model that is simpler minus the model that has more parameters. And that holds regardless of whether you're working directly with -2 times the log likelihood and taking the difference, or taking the difference of log likelihood and then multiplying it by -2. The end result of this needs to be a positive number because that end result is treated as a chi-square. Degrees of freedom also needs to be a positive number. That's by how many parameters the models differ. And you can find exact p-values for these chi-square tests in a variety of ways. In homework 1, I would recommend using chi-dist in Excel, or you could build functions in R or something like that to do it for you, but there's no data to operate on, so the usual methods are not going to work. Yeah. I do remember vaguely talking about this. It might not have been last time, it might have been a different time. But in terms of how we talk about differences in fit, if you add things, what can happen? What are your choices? Model fit is better or not better. If you take things away, then it's what? Worse or not worse? Yeah. And that, the latter kind, I'd say, is not as common, but you do see it a lot in certain contexts. So structural equation modeling, the test of whether your factor structure adequately represents the patterns of relation in your data, that's a is it not worse comparison. Likewise, if you do measurement equivalence testing in a structural equation modeling framework, you start with a model where all the terms get to be different across groups and you gradually make them the same. You're looking for not worse in that context as well. Any others that you can think of that fall into the not worse kind? Those are the two that came to mind for me. Yeah, less common, but in this context, unstructured is the answer key. So we can compare everything to it and see if it's not worse as the goal. Other pieces of information that will show up that we can use to decide on relative model fit is AIC and BIC. And in your homework, I have in bold font how I want you to handle the computation of these things. The SAS way. So AIC has -2 log likelihood as its root, as does BIC. So that means smaller is better for these measures, always. They have a penalty function based on model complexity. So 2 times the number of parameters goes into AIC, and log of some kind of measure of sample size times number of parameters goes into BIC. And I have learned through trial and error that different programs interpret this differently. So in SAS, for instance, number of parameters depends on whether you're in ML estimation or REML estimation. If it's ML, it's all the parameters. So model for the means plus model for the variance, all the fixed effects, all the variances, all the correlation terms, etc. If you are in REML, it's on the variance side only. So only stuff that goes into building that variance covariance pattern would count. And part of my vocabulary drill was wanting to make that point, so I decided to have you stay in that method of computation. In terms of sample size, this varies across programs too. So it is level 2 sample size for the BIC, so natural log of sample size at level 2 is what you get out of SPSS, I think, SAS, and I found a new R package I'm going to show you called MMRM, but it's total sample size across level 1 and level 2 in Stata and in NLME by default. So this would give you a headache if you're looking at output from different programs and trying to make comparisons. But if you stay in one program and it's internally consistent, then you're fine. Because these numbers have no absolute meaning. It's just smaller is better relative to each other. So what I will recommend in homework 1 is to build yourself a spreadsheet with these formulas, because the math is not the point. The point is for you to recognize, given this description of a model, how many parameters must it have. That's the point. Okay, now we're ready for slide 8? Why not? Okay, thank you for that emphatic nod. We're ready. Yeah, yeah. So, the unit we are in is focusing on longitudinal data that are fluctuation, not change. So studies of things like stress or mood, where you might have momentary disturbances, but there shouldn't be like continually increasing stress or continually decreasing mood or things like that. So we're going to be looking at 2 things. Are the variances the same across time or different? The default for most of these patterns is going to be same, homogeneous. Heterogeneous is the alternative. That means all the variances get to differ across time. And then covariances, are they the same or different? And if different, what kind of different? And the trick with this is that sometimes your model output will be phrased in terms of covariances, and sometimes it will be phrased in correlations. That differs across programs too. But I can tell you that for heterogeneous variance models, it has to be phrased in terms of correlations. Because if your variance differ over time, so does your covariance for that reason, regardless of whether there's a constant correlation. So those patterns are built constraining correlations into patterns and then extrapolating them into covariances given the different variances. You may not need any fixed effects for time. So if like stress is not systematically increasing or decreasing on average, a fixed effect for time isn't going to have anything to do. Like it's just a flat line. So in the example that I'm going to show you, there's no effect of time in the model. It's just a standard fluctuation exercise. Limitations for these, a lot of them require equal interval occasions. If they are phrased in terms of some kind of time lag, that will be the case. So if you have unequal intervals, you will need to adjust for that if possible. You can do so if you're using AR1. We'll talk about what that means in just a second, but not so much some of the others. So equal interval would be like each occasion is 1 week apart, or 1 year apart, or 1 month apart. If you have something like pre-test is time 0, and then the next occasion is 3 weeks later, and then the third occasion is 3 months later, that won't work. That's not equal interval. Because then if you're talking about like a lag 1 relationship, the distance between the two, you wouldn't expect the correlation to stay the same if the distance is not the same as well. So things that are specified in terms of lags, you'll hear me say that repeatedly, are requiring equal intervals. Many of them also require balanced time. Yes, sir.
Sorry, Lisa, I have a quick question.
Please.
So, balanced and equal interval occasions are not synonyms, right?
That is correct. Balanced and equal interval are not synonyms. Thank you for bringing that up. What's balanced mean? Nope, that's incomplete.
Oh.
Those are 3 different things. I know. Yep. Yeah, should we re-go over that? Yep. So we have, well, we'll start with the easiest one, complete versus incomplete. If you have any missing data, it's incomplete. Okay. The rule is you get to use all occasions that are complete. That's the rule. So if you have somebody who gave you 3 out of 4 occasions, you use the 3 that you have. So long as you are in estimation using some kind of likelihood. If you are in least squares, then you don't get to keep any of the incomplete occasions. Ordinary least squares, I should say. I know there's other kinds that are more tolerant of that. Then we have equal interval versus not. That has to do with equal distances in time between occasions. That is only a problem if you're fitting a correlation pattern that's built with lags. And there's a couple of them that have that. We'll see examples of that. And then last but not least, balanced. What does that one mean versus unbalanced?
Someone tested seen for 3 times, other for 5 times, other for 7 times. Something like that.
That is sometimes what it means, but I'm using it more specifically than that. Like in a clustered design, like if you have different cluster sizes, they would say it's unbalanced for that. But I'm talking with respect to time specifically. So I'm adding an extra set of constraints on that. What does balanced mean in the context of when people are measured? The same times. Everyone's on the same schedule is what balanced means. So if you show up at a school in the fall and everybody gets measured that one day, and then you show up again in the spring and everybody gets measured that one day, that's balanced. But if fall takes 4 weeks to get everybody done and spring takes 4 weeks to get everybody done, then the actual distance between occasions is going to differ across people. So they're on different schedules, essentially. And the structures that are built in terms of rows and columns being discrete things, they require balanced. Okay, does that help? Yes.
Thinking of that example of fall and spring, that brings me again to the equal interval thing. So how's that differ again? So it sounds like fall and spring, like let's say, so according to your previous example, fall has September to December, but some students come to September, but other students come to November. Then isn't it about the equal interval, not unequal interval again?
I think that unbalanced data is most likely to be unequal interval too, but not necessarily. Okay, I know. I know.
If you had to like take a test 3 months after or something like that, like if
Mhm.
3 months started in October versus September, it could potentially still be an equal interval between measurements, but then it wouldn't be balanced because not everybody was measured the same day.
Yes, yes. So let me repeat that for the audio and for the Zoomers. So let's say if I extend that example, some kids are measured in September, exactly 3 months later you come back and measure them. Other kids are measured in October, exactly 3 months later you come and measure them. I would call that unbalanced because like when they're being measured is different, but it's equal interval within a person. Because if you're trying to stitch together like what a profile would look like across the school year, and only some kids are contributing to the September part and other kids are contributing to the October part, then they're not on the same schedule. And you might expect differences because of when they were actually measured, beyond just how far apart in time those measurements were. So what I would do in a case like that, by the way, is the first occasion is time 0, I don't care when it was. And I would keep track of how long it's been since time 0 happened for each child. Then as a child level piece of information, I'd be like, was time 1 in September, October, December, January, expecting that kids who were measured later might look better at their first occasion because they've been in school longer. That's how I would address that problem. And I would do the same thing if you had an accelerated design where say you start with like 3rd, 4th, and 5th graders and you follow them over time. I would have a person level predictor for whether they started in 3rd, 4th, or 5th grade, but then that is time 0 and you follow them from that point on. That will be a topic in the spring class. That's one of the first things in the advanced class. Because those models are a little trickier, as you might imagine. Age and time. Okay, other points of clarification we can help with, or comments?
Can we say that balanced is a term that we can only apply across the whole data set, but equal interval is a term that we can apply for each individual unit?
Yes, I would agree with that. So she said balanced is a term that we can use to apply to the whole data set. Equal interval could apply to specific people, or not, and I think that is true. A lot of the time in fitting these models, particularly for folks who are using SEM to do it, structural equation modeling, they pretend stuff is balanced. I do not recommend that. Because essentially you're rounding time into convenient intervals, you're introducing measurement error in when they were measured. And that's generally not advisable, right? To add error to your data on purpose. Did they frown on that over in statistics?
I'm not sure.
You are sure, you're in that program too, right? Data science?
Yeah.
Do they encourage adding measurement error to our variables?
Oh, no.
No, I didn't think so. Yeah. Don't want to overgeneralize, but that seems like a bad idea. The trick is because in the software, it makes you. So like Lavon, for longitudinal models, has no way to introduce unbalanced time. I only know of 2 programs that do, M+ and OpenMX, which is, I think, embedded in R now, but it used to be its own standalone thing. You have to specify everything in it in terms of matrices. So it's not the funnest thing to work with for me. as someone who does not enjoy matrices all that much. Despite what Unit 4 is about, nothing but matrices. And new terminology. So we're starting with everything in one matrix. The R matrix is what I'm borrowing SAS's terminology, but I've seen a lot of other folks use it. The general rule with terminology is that you can use whatever you want, but you have to be internally consistent. So I'm following SAS documentation because that's how I learned this stuff initially. So R matrix is what I'm calling models that have the variance on the diagonal is per occasion, and it's leftover variance, mind you. I'm going to use the word residual very carefully. I'm going to say leftover when that's what I mean. So these are all leftover variances after the fixed effects have done their work. And there's a series of choices that I will call R-only models because there's no other matrices involved in creating the patterns. It is repeated in SAS. It is, I think, residuals in Stata, and it's various things in R based on which package you're in. We usually assume the R matrix is the same across people, but that's not necessarily required. There are models that allow different amounts of residual leftover variation as a function of person characteristics or time characteristics. Those are called location scale models, by the way. We're not going to get to those this semester either, but they exist. So our R matrix is going to be symmetric with dimensions of level 1 number of occasions, so I'm using lowercase n for that by n. And so that means that each person would have potentially a differently sized R matrix based on how many occasions they're contributing. When you ask for the R matrix to be printed in your output, you may have to find somebody in your data set that has complete data and ask it to be printed for them. Otherwise, you won't see the complete version. Other ones we're going to see 3 other letters that are going to show up probably next week or at the very end of today, and then I'll pretend that I never said it and we'll do it again next week too. G, Z, and V. More letters that are coming. So that's the second half, is these models approach it from more of a multi-level perspective, and there will be variances that have to do with people in G and variances that have to do with time in R, rather than putting it all in one spot. But that's forthcoming. Okay. So the models we're going to start with are only. Stata residuals is the option that we're using. There is a package MMRM something something repeated measures. I don't remember. It's a newer one. By the way, on our course webpage, I closed it, but you have it as well. I have links to all the different R packages that I'm using in the course. So you can go up there and find the documentation if you're curious about anything. And in SAS, we're talking about the repeated statement. So they are explained by showing the overall predicted R matrix, which is trying to recreate the total variance and covariance that is left over across occasions. So on the diagonal will be the total leftover variance. On the off diagonals will be leftover covariances. And in the descriptions that follow, I'm using the labels that SAS uses, but on our example, I have it annotated for each program in terms of what it would look like. So the tricky thing about this is that sometimes in the output, it gives you the ingredients for how to build the pattern, and then some packages just only show you the pattern. SAS gives you the ingredients always. R doesn't. You got to dig for it. So this is more complicated than it necessarily needs to be. Correlations can always be calculated. So if you're given variances and covariance in R, you can make a correlation version, and I'm going to call that R-core, where you would have ones on the diagonal instead of the variances, and then you would have correlations on the off diagonal. Critically unstructured is the answer key. So this is everything gets to be what it wants. It will fit the best according to -2 log likelihood, and everything is nested within it. So we can always come back to this as a comparison for balanced data. This is equivalent to a test of absolute model fit, as you would have in structural equation modeling, because this is the right answer. The goal is to find a model that is simpler but not worse. And I have a note that Stata users, you're going to have to wait a minute for unstructured to estimate. I don't know why, but it takes disproportionately long in Stata relative to other packages. Beats me. All right, so let me back up for a second here. Go back. There we go. I'm going to introduce a disclaimer. Can I do that? This is not my favorite topic to teach. talking about matrices and correlation patterns is not theoretically interesting. No one ever wrote a grant that said, I'd like to find out in AIM 1 what the proper correlation matrix is, and in AIM 2 I'm going to do this. No, NIH is not going to give you money for that. I can give you a couple examples of, like, in real life, like what this would be analogous to, and I can try to make the correlation patterns a little more relatable. So you give me a little bit of a leverage for that? Okay. So how many of you have had the misfortune of trying to paint a room in your house or apartment? Couple folks? Painting, yeah, Zumbersu. Painting is not just you go to Home Depot, you find the color that you like and you put it on the wall, right? That is the quickest way to a crappy paint job. No, painting is like first you have to patch all the holes and then you sand them and then you need to take all the outlet covers off and the light switch covers and then you need to tape along the baseboards so you don't get paint on your baseboards and on your carpet, and then hopefully you'll tape the ceiling for the same reasons, maybe tape around a window. My first house that I got, I decided to paint a bunch of rooms and I was terrible at it and I was really surprised at how long everything took. The same thing is true, by the way, as a slightly more gendered example, nail polish. You don't just pick out a color and slap it on. Your manicure is not going to look the best it can. No, you need to cut things, you need to file them, you need to smooth them, you need to fix your cuticles. Like, there's a whole process. And I happen to be pretty good at painting my nails. And so I just, like, once I started painting rooms, I'm like, actually, this is kind of the same thing. So I liken this process of going through and trying to figure out what pattern best matches my data as the priming, prepping process for analysis. It's not the fun part, but it's necessary to have everything turn out the way you want. The big picture is that the standard errors for all of the fixed effects that we care about are predicated on getting the model for the variance as right as possible. So before we start throwing in the predictors we care about, I want to make sure that we've adequately represented the patterns of variance and covariance so that they're tested as accurately as we can. And we don't know what the right answer is unless it's unstructured, but we can make reasonable guesses by comparing the fit of alternative things. And this would be a case where after you're all the way done, you might recheck these steps to make sure that you're still landing at the same spot. Okay? How's that? Fair. So the other way that I talk about these things, in terms of structures, to give you something to hang on to, is styles of pants. Yes. Unstructured is like sweatpants. Athleisure, they will always fit. If your sweatpants don't fit, something went wrong. Like, sweatpants are meant to be big and comfortable and soft and easy, and you can sleep in them or you can take your garbage out in them. If you're an undergraduate, you come to school in them. Sweatpants will always fit. Like, that's unstructured. Here's another one that you already know. Compound symmetry. We've done a lot with this one. I'd say this is like skinny jeans. Skinny jeans look perfectly fine on some people, not so much other people, and you will never ever see me in them. I don't like pants that cling to my legs. That's just a thing that makes me go, I don't like tights, I don't like leggings, I don't like any of that. So I draw, like, this is a pattern that is somewhat restrictive, just like skinny jeans and leggings are. It's saying that all of the covariances over time are the same, and all the variances over time are the same. What you get on your output varies by package for this one. So in SAS, it gives you the variance of the residuals and the CS, this piece, as the variance of the random intercepts. That's the same thing. So you add them together to get the total. In Stata, it just gives you the total instead. So you got to work backwards to figure out how much is because of E. If you say, okay, well, reasonably constant correlation over time could work, but I want to have different variances over time, that's CSH, compound symmetry heterogeneous. This one, I believe, does not exist in Stata, but I found it in R, and it's in SAS as well. So note the parameterization on the bottom here. We have a total variance at each occasion. We have CSH as a common correlation, which then gets multiplied by the standard deviation of each corresponding occasion to create the covariance that goes with it. So the CSH is locked down. The variances and their corresponding standard deviations can vary across occasions. So different variances, but a common correlation creating different covariances within these choices. There's two options for you. These two, I think, would also be reasonable for other kinds of multivariate data. So like if you have an experiment and people provide data for you in conditions A, B, and C, I think these structures would be reasonable for that kind of data as well, because you can say, well, there's an equal correlation because it's from the same person, but maybe condition C is harder, so it has more variance than condition B or condition A, something like that. Okay, so skinny jeans / leggings for this one. AR1, autoregressive, first order autoregressive on slide 12. This one is tapered pants. Tapered pants start normal, but then they get very, very skinny towards the ankles. And I used to watch a show called What Not to Wear. Any other fans of that show in the house? Yeah, Stacy and Clinton. They hate tapered pants because for most people they are very unflattering. They make the top of you look like disproportionately wide because of the narrowing. And they always want to get people in straight pants. And most people that they had on the show looked better that way. So the problem with AR1 is the same problem as tapered pants. It gets too skinny too quick. So there's only two parameters in this model. There is a variance that is the same over time. So that's what T means for total. Note that it is not divided into U and E. Okay, this is not a multi-level version of a pattern. This is putting everything kind of in one basket, so to speak. But it does still allow dependency, correlation of occasions from the same person via this one R parameter. So R to the first is how correlated 1 and 2 is, 2 and 3 is, 3 and 4 is. So if you look on these are called bands right here, if you follow my mouse. The diagonal band is the variances. The first off diagonal is known as lag 1. So occasions that are 1 unit in time apart are correlated to R. Occasions that are correlated are 2 units in time apart are correlated R squared. 3 apart, R cubed. Can you guess what 4 would be? R the fourth, R fourthed. Why doesn't that one have a verb? Squared, cubed, fourthed, fifth, sixth. It seems like it should be a thing, but it's not.
Quadruple. Quadruple?
Yeah, that's like times 4 though, like,
Okay.
yeah. Anything?
Yeah, I think quadruple.
Quadruple?
Yeah.
Okay, quadruple it is. So there's only one R. And you square it and cube it and fourth it and fifth it to get the rest of it. And what happens is that R makes the correlation die off really quickly. So occasions that are far apart in time are not predicted to be correlated. And that just doesn't happen in longitudinal data. There is always a correlation of occasions from the same person to some extent, even at distant occasions. So I have yet to see a data set that fits this. Yet. It only has 2 parameters though, regardless of how many occasions. This version right here is constrained to have equal interval occasions. The AR1 model, like the default version of it. Because if you think about it this way, like if this is every week for a month, then week 1 is just as correlated with week 2 as 2 is with week 3 and 3 is with 4. Like if they're equal interval, that's a reasonable thing. But if it's like 1 week apart and then the next one is 3 weeks apart and the next one is 3 months apart, like why would 1 and 2 be as correlated as 2 and 3 when 2 and 3 are separated by a much longer interval? So equal interval is required to have this lagged pattern make any kind of sense. Fortunately, there is a workaround. I found it in SAS and in R, not in Stata, that allows unbalanced time. So there is patterns by which you can specify a continuous time variable and introduce the same type of relationship where it understands how far apart the occasions actually are. But tapered pants narrows too much, too quickly, so does an AR1 matrix. And I would not present this at all, except that this shows up in structural equation models for longitudinal data quite frequently. Have you seen a path model where you have like a time 1 box predicting a time 2 box predicting a time 3 box? And these are constrained equal? That's this. Cross-lag panel models in particular have an X that each one is predicting the other, the Y that's predicting the other, and then like this in the middle, last times X predicts next times Y. Those models expect this pattern to be true. Do you remember the part where I said I've never seen this pattern hold in real data? Yeah, that's why I don't like those models. They are demonstrably false for many kinds of longitudinal data, but they show up in other contexts, like agricultural contexts, like StatStat may have data that follow this pattern, but with people, nope. But you can expand it to have heterogeneous variances. So you can add an H to make the variances different over time, but then we have the same R to the first, R to the second, R to the third pattern building in the correlation structure. Okay, one more, then we'll see an example. One more slide, I should say. Topolits, which I always say wrong. I always move the E. I say topolits, it's actually toplets. I can't fix it, it's just topolits. Taupe, for short. This one is another banded pattern that pays attention to lags. So we have a constant variance on the diagonal, and again, this is not split into between and within. It's lumping everything together, but it is still allowing covariances. This one I like to call bootcut pants, because bootcut could mean like flared out a little bit, or it could mean straight. It just depends on your manufacturer. And this one is similarly flexible. So the way this is specified is that the first off diagonal here, lag 1, says all these covariances should be the same. If it's 1 unit in time apart, this is how related it should be. Boom. And then a second off diagonal says if it's 2 apart, this is how related it should be. If it's 3 apart, this is how related it should be. But these 3 sets of C's are separate. They're not like squared, cubed, fourth, they're just 3 separate things. So that means you have as many parameters as you have occasions to fill up this matrix all the way. Because if I have 4 occasions, then I have a variance on the diagonal, and I have lag 1, lag 2, and lag 3. So occasions 1 and 4 would be the only instance of lag 3. What it's called varies across software, of course. It's lag, what goes in parentheses here is n in SAS, and it's n minus 1 in Stata, because Stata doesn't count the variance on it. It only starts counting from here. So just little things that you'll see that make things more tricky than they need to be. And then, of course, there's a heterogeneous version, which allows different variances over time. So that would be as many variances as you have occasions, plus as many off diagonals. And note that because the variances are different, that we're switching to correlations here. You can't hold the covariance constant if the variances are different, but you can hold the correlation constant that contributes to the covariance. There. How are we doing so far? So we got sweatpants, always gonna fit. Skinny jeans, fit some people, not others. Too tight though. Autoregressive, tapered. Correlation dies off too much. And then bootcut, because you can have it be straight, you can have it flare. Like there's no restriction that these C's are ordered. You could have lag 3 have the highest relationship and lag 1 have a lower one. Like that's allowed. They're just 3 separate estimates. Want to see an example? Why not, right? We'll roll through these. This is a real-world example. The data are not in your download folder. So I did a different data set in Chapter 4. I had built this example a long time ago, so I decided to revisit it and adjust it to make sure that we have all the packages operating in here. The last time I did this, I only showed SAS because of all the weirdness across packages, and I decided to suck it up and fix it for y'all. So this is a true story. These are data I helped collect, actually, in graduate school. This was a friend of mine who was part of a large grant and hired me for their project as a GRA. This is the same person that I built the Heartland Forgiveness Skill with, actually. So you'll hear all about that if you take the SEM class. And still, Internet, you have my permission to use the scales. You do not need to keep sending me emails. There's one scale that is by far the most cited thing I've ever helped with. The first author is no longer in academia, the second author is dead, and I'm third. So I get at least 3 emails a week of people saying, can I use your scale? I'm like, it's not mine, go ahead. Like, it was published 20 years ago, knock yourself out. So these data, though, were not published. This is part of a dissertation. So the story behind this is that, so my friend is a clinical psychologist interested in positive psychology, forgiveness, coping skills, that kind of stuff. And she was interested in the role of stress and coping skills in the outcome of psoriasis severity. So psoriasis is a skin condition, has itchiness and scaliness and some discoloration, and it's thought to be exacerbated by stress. So this is an example of an outcome that would be related to stress, potentially differentially across people. Like if you're a better coper, potentially stress doesn't affect you as much. That was sort of the goal. So she walked into her dissertation proposal with this lovely cross-sectional design. Her husband is a dermatologist, so she can get some clients who have this condition pretty readily. She had her measures lined up, and by the time she walked out of her dissertation proposal, her study had been redesigned by her committee to include a longitudinal component. This. Over an 8-week period in the summer, yeah, she's like, can you do that? They did that to her, yes. Over an 8-week period in the summer, myself and several other research assistants stuffed packets full of questionnaires, mailed them out to the participants, had the participants mail them back, hand entered all the data into Excel. Good times. Yep. And when all was said and done, this is what we got back. So this picture is a plot of individual trajectories, is the fanciest way to say that. This is also commonly known as a spaghetti plot. Because if you take a handful of wet spaghetti and throw it at a wall, this is kind of what it looks like. Colorful spaghetti, though, you know. Rainbow colored spaghetti. The black line in the middle here is the mean. So this is not a treatment study. These are people that are being treated as part of their normal life experience, but there's no reason why being part of our study and filling out our questionnaire should change their disease status. So this is fluctuation. Some weeks are better than others in terms of how their skin is behaving, and some folks have higher severity all the time, and some folks have lower severity all the time. So that's the story. So we were trying to figure out how to analyze these data, and I knew enough to know about growth curve modeling. And I remember taking this data set to, I was a Penn State postdoc. We had this thing called Methods Lunch, where it was like brown bag, you bring your lunch, and each week someone volunteered to present a problem, and everyone that was interested gave advice. And it was like a really great thing because they frequently disagreed with each other. So getting to hear people fight about why they thought it should be this way versus that way was very instructive to the rest of us. So I showed up with these data, and I'm like, it's longitudinal, but it's not growing, and I know growth curves, like what do I do with it? And Mike Rovine, a person whose classes I audited, raised his hand and said, just don't put time in. What? Just don't put time in. If it's not changing, don't put time in. It's still a multi-level model. You can do that? Yeah, you can do that. So we're going to do that. Time doesn't help you if there's not change. This is just fluctuation, right? It doesn't matter whether it's week 8 or week 7 or week 6. It matters what's happening in their lives during those occasions. Now, if it did matter, if there was reactivity to the measurement process, that would be a different thing. Like if they got tired of filling out the questionnaires and they answered differently as a function of that, then that's a different problem. Yes?
Would you figure this out by doing an interclass correlation to see if or how do you know? Do you just have to look at the visual and then you know that you don't need to put time in?
I plotted the means, I plotted everything, and it just there's no change. And this picture I think shows there's people who have a lot of variability, but there's not something systematic that is sort of like everyone is following in the same direction.
Okay. So there's no one test you can do to decide if you need.
I don't think so. I mean, ultimately what you can do is compare a model that has different means over time to a model that has the same mean, and you can see if adding those extra different means helps you. That would be does the main effective time, is there a significant omnibus effective time from a saturated means model? Or you can fit, different kinds of time slopes, linear, bendy, etc. But yeah, there's no change in this. Yep. So let's see the answer key. And because I knew this was going to be a lot, I highlighted the things that change. Is that fair? It's the same code every time with like one word switched. So, unstructured. And I'm including SAS in here because there's certain combinations I can only get from SAS. So you get exposure to that. So proc mixed is everything in SAS, the same way that mixed is everything in Stata. It needs to know what data set you're using. It wants to know what you want to be printed. So code test adds standard errors for the variance components. This thing shuts off extra output. This adds information criteria, more by default. And then method equals REML. Can you guess what that does? REML estimation. REML is better for smaller samples. It gives you unbiased variance components, whereas those from ML will be too small once you get to level 2 variances. Sub ID is the name of my level 2 identification variable, and week is the name of my level 1 identification variable. And I am using only weeks 2 through 8 of this data set because one of the things that her committee wanted her to examine was if stress the previous week is affecting you, does that translate into worse psoriasis? I've made up a new word again. Psoriasis severity in the next week. That was one of the questions. And it turns out it does at p less than like 0.04. So she did have a finding with this, but that's a different example. So I'm looking at severity. Model is where you tell it what you want in the model as an outcome variable, and then predictors would go here, and there aren't any. So these are empty means models in every case, because there's no change. Solution means give me the answers. That's not a default, believe it or not. And Satterthwaite is the denominator degrees of freedom method that we're using. Doesn't matter for this case, but I keep it in all my programs anyway. Repeated is how I tell it what kind of R matrix I want. Week is the ID variable that tells it which row should go into which row of the R matrix. So this is necessary with missing data, which we do have. So if somebody has like weeks 2, 3, 4, and 7, if I didn't tell it to use week, it would be like, I'm going to take 7 and stick it into the next one. It'll go where 5 goes, because it doesn't know that it's 7 and not 5. So this variable makes sure that the right rows of your data go into the right spots in your matrices. Type equals UN, that means unstructured. R and RCore means print those for me, please. And then how do you want them organized? By subject. That's my level 2 ID. Just like in R, how you save the results of your analysis as an object, and then you can go dig in and find the numbers for it and make it do math on those. SAS has a system called ODS output that does the same thing. So I am saving an internally named table that SAS calls InfoCrit, which is the log likelihood value, number of parameters, and all that, to a data set in SAS that I've named FitUN. And I'm doing that so that I can then take that information and feed it into a likelihood ratio test. And this is a macro that does it, macro program that I wrote. In the SAS files that go with this, you just have to run that program and then you can use it. So it just does the math for you, more simpler. Okay, any questions on that? Stata folks, we are still using no random intercept in these models for right now. And instead, we are focusing on structuring the R matrix. And the residuals option in Stata is how you tell it that. Unstructured, I think you can abbreviate that UN, but I tend to write these things out just for my own sanity. And then T week does the same thing as week up here. It makes sure that the right rows of the data go into the right spots in the matrix. The rest of this you would have seen already. REML is our estimator. No log means suppress the printing of the iteration history. And difficult is something I discovered fairly recently. In Stata, there's an option if the estimation problem is difficult. If you throw this in, it somehow approaches it differently. So like superstitiously, I just started sticking this in anytime things don't converge. I'm like, is it going to help? Let's find out. So I don't know if it helps or not, but I don't think it hurts. These models can take like hours. Seriously, I don't know why. But when I figured this out when I was making the Piles of Variance website, all the differences across programs and how quickly things run. All right. More stuff. These commands here give you the predicted R matrix and R correlation version. These commands give you AIC and BIC. And then estimate store, I'm asking it to save the results of this model under an object called fit-UN that I can then use for a likelihood ratio test against other models. This should not be there. That should look like that. And then R. Okay. So I was all excited when I found a new package that I had not seen before called MMRM because it was specified in a way that I thought was way more intuitive. And then I started finding the downsides of it. I tried to go with it for some of the ones that are easy enough. The first thing is that it insists that your ID variables are factor variables. They weren't, so I turned them into them. That means they're being treated as categorical. So in this package, it wants to know what data set you'd like to use. Formula is your model. So severity and then squiggle 1 means I just like a fixed intercept, please. And then plus US for unstructured. Every other package is like it's UN. Nope, it's US. And the structure is my new factor version of the weak variable, bar, and then the new factor version of my level 2 person ID variable. Underscore REML equals true, saying use the REML estimation instead of ML. If you wanted ML, can you guess what this would need to be? False, yeah. So it just varies by package how you tell it what you want. And then I'm asking for it to print deviance, which is also a synonym for -2 log likelihood. You will see that in other places as well. The summary of this model, so I'm saving it as a name UN, and then I'm adding R core via a separate function that I found that turns covariance matrices into correlation matrices. Cov2 core does what it says. So I am showing R output for this case because the output for SAS and Stata is nearly identical. This is not a pattern, right? This is unstructured. This is everything gets to be what it wants. So there's not like a common set of ingredients that build a pattern out of it. This is just, how many variances do we have? If we have 7 occasions? Not a trick. If I have 7 occasions, how many variances in an unstructured matrix? 7. How many covariances? Yeah, 21. So that's where we get down here. It tells you 28 parameters to fit this thing before we even start talking about stress or any of the other things that she cared about. Note that I have 770 observations from 124 subjects with a maximum of 7 time points. So some unbalance in the data, but a lot, mostly complete. So in here, it gives you log-like, which is LL, and then deviance is -2 LL. Question?
Yes, I have a quick one, Lisa.
Yeah, hit me.
If we say that the variance of the residuals is a model parameter, why is not counted there?
So there is no single residual variance in this approach. There's 7 of them. So this is not dividing it into between and within. This is total. Everything's in one spot. So this is, remember, this is the multivariate repeated measures ANOVA analog. So it doesn't care or know that these are 7 occasions of the same variable. It could be 7 different outcomes, each on their own scale, in which case you'd want to have a separate variance for each for that reason alone. Yeah, yeah. This is a MANOVA essentially, but with REML, so that we can have not listwise deletion and have other cool stuff. By the way, the MANOVA, what is it called? Like the Wilks lambda and all those tests, those are likelihood ratio tests. They are. They're the same thing. I can prove it to you if you care, or you can just believe me. Jonathan figured that out like 15 years ago. So my fixed effects, there's only one. 1.5 is my fixed intercept. This measure, by the way, has been log transformed because it was very positively skewed. So on a log scale, that's the average amount of psoriasis severity in the sample. We're not going to worry about that from here on out. The interest is in the variance patterns and covariance patterns. So here is the result. The diagonal has what the variance was estimated to be under an assumption of missing at random. So it's trying to recreate the numbers that would result had the data been complete. What do you think of these? Do these look the same or different? This is an eyeball test. Mostly similar, maybe a little bit of wiggly.
2 and 7, something's going on, but the rest of them are.
Yep, 2 and 7 look a little bit off. I believe week 7 was near the 4th of July, actually, so that could somehow be a thing if like air pollution makes your skin worse. At least in Nebraska it does. No, Nebraska 4th of July is no joke. It is a war zone. Everyone is blowing up everything. Like it's all legal and everyone looks the other way. No, it's insane. If you ever get the chance to do a Nebraska 4th of July, you should, because you're not going to bed before midnight, because it's just like a war zone. Not so much here, but. Question?
I said it's not untrue.
It's not untrue. Have you been to a Nebraska 4th of July?
I've lived in Nebraska for many years.
It's crazy. Like it's just nuts. People spend like thousands of dollars blowing shit up. Proudly. Off diagonals or covariances, those are hard to judge because they vary with the variances, but I've got the correlation version down here. What do we think of these correlation patterns? Same or different over time?
They decline a little bit over time.
Decline a little bit, like not entirely consistently. So like lag 1, if I look at that, that's 0.9, that's 0.9, that's 0.9. Lag 2 is 0.86, 0.8978. Now, are these correlations large or small? In a correlation metric, these are relatively large, right? So do you know what that's going to translate to into, say, an intraclass correlation? You can think of an intraclass correlation as the average correlation over time from this matrix. Yeah, let's see what that is. So this is what we're trying to reproduce, this pattern right here. Variances and covariances over time. So let's start with the simplest option, compound symmetry. This is the multi-level partitioning into between and within, U versus E, we saw before. In SAS, it is type equals CS to accomplish that. Everything else is exactly the same. And I had to print some SAS output because I couldn't actually get the other programs to show me what I wanted. So one thing that SAS does is it gives you this little table, and it's called covariance parameter estimates. That's actually a bad name. This table should be called model for the variance parameter estimates because these are variances, correlations, and covariances. So the first thing that it gives me is the CS parameter, and as I have notated out here, that's my random intercept variance. 0.68 is how much of my total variability is due to between person mean differences. That's the amount of random intercept variance. We'll get to the proportion in just a second. Residual is my E variance specifically. So under this parameterization, the total would be found by adding these two numbers together. That is different, skip over this for just a second, than how it's set up in Stata, in which compound symmetry is called exchangeable. That means it doesn't matter which occasion it is, they're all correlated the same. You can exchange them. And Stata, I think we had this before, but I'll reiterate, gives you different information. What it labels as var E is not var E. It's total variance. It lies. Job security. Cov E is the compound symmetry parameter, or variance of the random intercept. So the pattern that is being created by these two ingredients, I'm going to call them that, is right here. And this is what it looks like in R, which has CS. They finally agreed on a notation system that matches the rest. It's this one right here. So this is my R matrix. That diagonal is the variance of the E's plus the compound symmetry variance of the U zeros. And note the diagonal is equal all the way down, constant variance. 0.68, that's my random intercept variance or my compound symmetry parameter, take your pick. And if I want to turn that into a correlation, here's my R-core matrix. And this correlation has a special name, right? What's it called? Starts with an I. Intraclass, yeah, feel free to read from the screen, always. So this intraclass correlation is 0.84. What does that tell us about psoriasis severity over a 7-week period in this sample?
Observations from the same person is correlated by 0.83.
Yep, on average, correlations from the same occasions from the same person are 0.84. I think you could also find that if you took the time to average over all the correlations in this matrix, like functionally that's what we've done, is say, hey, what if they're all the same? How well does that fit? Talk about it in terms of between versus within. Go down, come back.
Between person variation accounts for most of the variation in the study?
Yeah, 84% of the variance is because some people have worse psoriasis than other people, period. Let me put this a more cynical way. This study is an 84% waste of time because she has a cross-sectional study she had planned in which she looks at differences between people, and the benefit of the longitudinal was going to be differences within people, but that's only 16% of the information here. Their longitudinal study was an 84% waste of time. That's how I would put it in this context. This, I'm not going to say this disease is stable. I'm going to say the way people answer the questions about their disease is stable. I don't think we can make a distinction based on self-report data. Now, is this good enough? Does this match the unstructured matrix sufficiently? How do we know? Log likelihood, AIC, and BIC. Yep, this is a nested model comparison because unstructured had 28 parameters. By putting constraints on them, you get down to the 2 that this one has. So that should be a savings of 26. And this R package does not play nicely with ANOVA or RANOVA or any of the other ways to do likelihood ratio tests automatically. So I did it myself. So I saved an object comparing the deviance of compound symmetry, minus 2 log likelihood, minus that of unstructured. So note the order, fewer minus more. Printed it. Then I figured out the number of parameters in something called JACList. I know, I had to do a lot of digging to figure this out, and I have no idea what a JACList is. It sounds vaguely pornographic, to be honest. So I found the degrees of freedom that way, and then I fed it into a function for a chi-square test to give me the p-value. And the end result is shown a couple other places in here. Here is my macro that I do in SAS. I have objects within this for the fit of the model with fewer and the fit with the model of more, and then you feed it into the macro and it spits out this little table. So a savings of 26 parameters. The test statistic comparing the minus 2 log likelihoods of CS versus unstructured is 156, and the p-value is 0 to many decimal places. So how do I talk about this? Relative to unstructured, a compound symmetry model fits worse. Yep. It's too simple. 2 is not good enough. In Stata, do I have it printed? No, but this LR test command would do that exact same thing, and that is in the output on the online files, so you can see that. Okay, questions so far? How about a different one? So that one is skinny jeans. Skinny jeans fit worse than sweatpants. How about tapered pants? Autoregressive. So AR1 in the type for SAS gives you this pattern. And I have output for that. AR1 lowercase, no parenthesis, in Stata gives you this pattern. And AR1, no parentheses, lowercase, in this R package as well. So SAS output gives me the ingredients. The other ones do not. Hang on, where did it go? Here they are. So I get something that is labeled AR1, 0.8955. That's the R that gets squared and cubed and fourthed and fifth. Residual. You would think that this means E variance, right? It does not. It means total variance. Because this model is not between versus within. This is not U versus E. Everything is in one pile, but we're allowing dependency via this autoregressive correlation. So building that pattern then, Stata labels the R row, seems reasonable, and it still labels the total variance as var E as well, but it's total. The pattern it creates is a little bit difficult to discern in the covariance version, so I'll start with correlation. So in the R output down here, where I have R core matrix labeled, so I have the autocorrelation parameter bolded here. This is the lag1 correlation, occasions from the same person that are 1 unit in time apart, so 1 week here, should all have the same correlation. If I take that 0.8955 and square it, that gets me the next one. 2 weeks apart are all correlated 0.8. Cube it, that gets me to 7.2. Fourth it, 6.4. Fifth it, 0.58, and then the last one is 0.52. So in the original unstructured correlation matrix, did you see any correlations as low as 0.5 in there? Not even close. So tapered pants narrows too quickly. Not going to fit the data, not going to fit your legs. Now, relative to compound symmetry, this model also has 2 parameters. They differ in that compound symmetry says there's one correlation and it's the same over time. Autoregressive says there's one correlation, but you square it, cube it, fourth it, and fifth it to make it go down over time. They both say that the variance is constant over time. So how can I compare autoregressive and compound symmetry if they're both 2 parameters? Can I use a likelihood ratio test? No, because there's no degrees of freedom. 2 minus 2 is 0, and there's no such thing as a chi-square of 0. It's not a thing. I can do AIC and BIC instead to decide between those because they're non-nested models. They're just 2 different kinds of correlation patterns that 2 parameters generate. The covariance then is built from that correlation. If I take that correlation and multiply it by the standard deviation at each occasion, then I will end up with this covariance right here. Relative to unstructured, how do you think we did? Bad? Yeah, I'll take bad. Let me find the output for it. Here it is. Not quite as bad as compound symmetry, actually, but still p-value that is 0 to 10 decimal places. So not so good. All right, there's 2 more on this family, and then we have the next one, but I think those are going to have to wait until next week. I know, I'm just as bummed as you, but class is over. It's 1:42. So you can start, the AIC and BIC Zimmers, that is correct. You can start working on your next formative assignment assessment if you wish, or you can put it off. I don't care. It's due Wednesday. How's that?
Does it cover like the Toeplitz models?
Big picture stuff, I'm asking about different R matrix patterns. So like list as many as you can remember kind of things. So.
We can like start it now and then save it and come back to it later?
Yes. Actually, ooh, that's a good question. I'm not sure if you can, yeah. Yeah, like you can see the questions and then type your answers into a Word document and hang on to them.
Okay.
You also can submit multiple times. So like if you decide to change your answer later, it doesn't have memory, so you'd have to repaste in your stuff.
Sure,
So for that
sure.
reason, I would recommend saving your answers offline anyway.
Okay.
So,
Thank you. Yeah, that's
is someone still holding office hours tomorrow morning? Survey says? Yes, Vladimir is. So And as he said last time, he's bored. No one's coming to visit him. So if you just want to come and talk through any of this stuff or review some things, he's happy to help, right? Yeah, don't leave him bored. That would be a tragedy. All right, folks, let me know if you need me. Have good weekends. I'll see you next week. Bye for now. Bye, Zoomers.